All right, so this will be brief, but it's sort of similar to what Max talked about. The idea here is that I want to have some periodic QMMM. What I mean by that is a QM entity that's just discrete. So I'm not talking about material science-like things where we're periodic across the whole QM, but a QM entity surrounded by MM, water, cyclohexane, whatever that may be, and make that periodic. So this HelPME library is something that I wrote a while ago, mostly focused at the MD world, but I'm aware of a few people using it in QM codes now, so I figured it might be worth advertising here, and a few people may be interested in it. So what we're doing here is partitioning the Coulomb operator into a short range part that dies very, very quickly. So any integrals over that can be screened easily. Any charges involved in that operator can have very short cutoffs. That's trivial to deal with in normal ways. This long range part then, that doesn't have a singularity, but it does still have a long tail. So that's what's going to pick up all the periodic part of the potential and the long range stuff. So we're not going to treat that using conventional methods. We'll treat that slightly differently, and that's what the HelPME library does for you. So in generally, what you want is just the potential at any given point in these calculations from the density, be that the exact density evaluated at some point in space or density from some point charge representation. And so we can solve Poisson's equation to get that. What we'll do is introduce a complex exponential basis because, as I said before, we want periodic functions, so trigonometric functions make sense from that point of view. But also, because the derivative of an exponential is an exponential, it means that the derivative operator just becomes a constant when you introduce that basis. So solving this equation becomes very easy. So the trick here in PME, this is what Tom Darden invented, who spoke yesterday. You discretize your system onto some regular grid. And so you may, in QM world, you may want to just evaluate the density directly on the grid. That's what you do in the Fourier transform Coulomb method that QChem uses. In MM world, you've got point charges at some random point in space. So you surround those with spline functions, use those spline functions to evaluate that charge on local grid points. So here I'm showing two atoms that are done that way. Forward Fourier transform this charge grid, and that gives the Fourier space representation. And as I hinted in the previous slide, this differential equation then becomes trivial to solve in Fourier space because this operator just becomes a constant, m squared, that you can divide by. From there, you have the potential in Fourier space, and an inverse Fourier transform gives the potential in real space, which is ultimately what you want for these QMMM-like methods and for MD itself. So this library takes care of doing all of that stuff for you. You just give it a bunch of positions and it handles the rest. We actually use it in Charm and a couple of other codes for doing dispersion PME. So if we're looking at 1 over r to the 6th kernels, this library can support it. It just generates the equations on the fly using some template metaprogramming. It's written in C++, but there are bindings for C, Fortran, and Python through the magic of PyBind 11. So any language you use, you can hook this stuff in quite easily. It's all templated, so if you want to do single precision or even long double precision, if you're feeling like it, then that's possible. Inspired by the Catch unit testing framework, I made it so that it can be dropped into a project just as a single header file. So if you don't want to mess with build settings and CMake and all those things, you can just grab it straight from GitHub, address is down here, and just drop it straight into your project. Very easy to configure. It's going to come into Sci4. There's a pull request that Laurie has open. He did some CMake magic for me, so we'll have it in Sci4 as a proper first-class citizen. Just like Max's library, arbitrary order multipoles are supported. So if you have potentials involving hexadecapoles or whatever, then it all works. Not really an issue for QMMM. I mean, these things run in the order of milliseconds. So any SCF you can do in milliseconds is not going to be very significant, right? So this will never be the bottleneck in QMMM world, but it's the bottleneck in MD world. So for that reason, it's got this 3D parallelization scheme that I will just advertise without detailing. Most importantly, it's got a very permissive license. So if this wants to be dropped into commercial software or any open source software, it's all fair game. And that's all I had to say.